As you move across the periodic table from left to right, the effective nuclear charge, or Zeph, is going to increase, which means we're adding more and more protons. And since the nucleus is becoming more and more positive, it's going to pull harder and harder on electrons. So the atomic radius, or the distance from one nucleus to another, is going to decrease as you move across the periodic table because there's an increase in the nuclear charge. As you move down the periodic table, you're adding more and more principal energy levels, and therefore you're adding more and more shells. So the atomic radius actually increases. Now, an exception occurs between the halogens and the noble gases. The halogens are the smallest in a period. The noble gases are larger. If the periodic trend is that the atomic radius decreases as you move from left to right, why are the noble gases larger? And this has to do with the valence shell. Fluorine have an orbital diagram like this. When we add another electron, making it neon, we have the maximum electron-electron pair repulsion, and this causes those electrons to space out further. Ionic radius follows the same general trend, but we need to talk about ions. Remember that group 1A has one valence electron, so it will become a 1 plus charge, cation. 2 plus for group 2A, 2 valence electrons. 3 plus for group 3A. Plus or minus 4 for group 4A, 3 minus, 2 minus, 1 minus. If we have less electrons, the ionic radius is going to be less than the atomic radius because now we have the same number of protons that are pulling on less electrons. But the less electrons we have, the smaller the radius will get. If we add electrons, the more electrons we add, the larger the element gets. So ionic radius, as you go from left to right, decreases until you get to group 14, and then, or group 4A, because then it will reset and then decrease again. This has to do with the effective nuclear charge, or Zeph, as well as the fact that you're holding less electrons. As you move down a periodic table, though, it's the identical reason and trend as atomic radius. That as you move down the periodic table, ionic radius also increases because I'm adding more and more valence shells. You cannot discuss ionic radius and noble gases because noble gases typically do not form ions. If you have something that is isoelectric, meaning that it has the same number of electrons, simply consider it, well, how many protons do I have? Fluoride and oxide both have the same number of electrons. They both have 10 valence electrons. They both have 10 electrons, 8 valence electrons. Which will be smaller? Well, fluorine has more protons in its nucleus, therefore its Zeph is higher. And therefore, fluorine will pull those electrons in more. Plus, fluorine is holding less extra electrons, and therefore has less radius, has a smaller radius. Ionization energy is the energy required to remove an electron from an atom if it's in the gaseous phase. And it's always going to be endothermic, meaning you need energy in order to remove that electron. Each electron you try to remove is going to require more and more energy. As you move from left to right across the periodic table, the effective nuclear charge, or Zeph, is increasing, and therefore it's pulling the electrons closer and closer in. As those electrons get closer and closer to the nucleus, they have less and less energy, and therefore it will take more energy to remove them as they get closer to the nucleus. So going from left to right, first ionization energy increases. As you go down the periodic table, you're moving further and further from the nucleus. The further you are from the nucleus, the more electrons you have, the more energy you have. Therefore, the less it requires less energy to remove you from the atom. And so as you move down the periodic table, first ionization energy decreases. We typically talk about first ionization energy because after the first ionization energy, it requires more than is possible, more than is probable or is available to remove a second or third electron, especially if you have to drop down in energy level, because then you're breaking into the core electrons. Now, several exceptions do occur within this trend. Whenever you are changing the angular momentum or the shape of the wavefront, so whereas this is S, D, and P, wherever there is a change in the shape, there is a drop in ionization energy. Now, why is that? It's because s orbitals are extremely close to the nucleus. Oh, sorry, let's focus on one at a time. Let's go from S to P. Beryllium's ionization energy is much, much greater than boron's ionization energy. Why is that? It's because s orbitals are closer to the nucleus. They penetrate closer to the nucleus, and therefore they will require more energy than a p orbital. If we go from an S to a D, and we're asked why is there a drop in ionization energy here, it's because we go from being, let's take calcium and scandium into consideration. Calcium would be 4s2, and then scandium would be 4s2, 3d1. Well, that 3d is actually up here. There's close, that 3d is penetrated closer to the nucleus than this 4s, and therefore this has more energy, and therefore can be removed easier. That 3d electron can be removed easier. Another exception to this, it happens at the D5 and D6, or at the P3 and P4. So between nitrogen, the nitrogen family, and the chalcogens. Why is that? Well, if we looked at the electron configuration of nitrogen versus oxygen, nitrogen would be helium 4s2, 2p3. It would have an orbital configuration of this, 2 ups and then 3 ups in its 2p orbital. Oxygen would be helium 2s2, 2p4. 2 ups in its s, and then up, 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 and then a down. This first pairing of this electron actually increases the electron pair repulsion. And that electron that's first paired actually has higher energy than any of these other electrons. And therefore that causes it to be easier to be removed. It has higher energy, it is easier to be removed. So when you're talking about ionization energy on the AP exam, you need to discuss those exceptions if you're asked about them. The general trend is that as you go from left to right, ionization energy increases because there's an increase in the nuclear charge, which is pulling those electrons in tighter to the nucleus, and they have less energy. As you move from top to bottom, there is a increase in the distance those electrons are from the nucleus, and therefore they have more energy, and therefore they are easier to be removed. They're easier removed. The last periodic trend that we have to talk about is electron affinity. And it's simply the liking, and I use the word very loosely because it's really just an affinity for electrons. It's how much energy is released when you add an electron to a neutral atom in the gaseous phase. And it's really not that big of a deal on the AP exam. You'll see it maybe as a multiple choice question and extremely rarely as a free response. It always is going to be starting as a negative quantity because energy is being released. It's exothermic. As you move down a family, as you move down a period, it becomes more and more negative. It becomes more and more positive because it gives off less energy because of an increased distance from the nucleus with each increased principal energy level. As you move across the period, it becomes more negative because the electrons are closer and closer to the nucleus. Meaning it gives off more energy. Exceptions occur within this trend when you begin your first pairing. If you force an electron to do if you force an atom to do a pairing, it's going to give off less energy. The final trend is actually not a periodic trend, it's actually a bonding trend, but we bring it in here because it's part of this unit. Electronegativity is simply the ability of an atom inside of a molecule or in a bond to attract the electrons that it's sharing in that bond. It's kind of a tug of war. It's based off of a Linus-Pauling scale, where 4 is the most electronegative and 0 is the least electronegative. Noble gases are given an electronegativity reading of 0 because they are very extremely rarely in a bond. Fluorine is given the most electronegative, which should tell you it must have something to do with size. Fluorine is the smallest, and you would be correct. Because electronegativity is driven by how well those electrons are being clustered around a particular nucleus, fluorine is the smallest, and its nucleus is nearest its valence electrons. The electrons can get closest to fluorine because it is among the smallest, and it will pull those electrons in tightly and hold on to them. If you are massive and huge, like francium down here, or cesium, you don't have much of an attraction for your electrons, and you have a hard time stealing or keeping them near you. And so francium and cesium have the smallest electronegativity. Nitrogen, oxygen, and fluorine are among the highest, with fluorine being the most. So as you move from left to right, electronegativity increases, but as you move down the periodic table, electronegativity decreases. It all has to do with how close those electrons are to the nucleus. So you will describe it in terms of effective nuclear charge, or Zeph, going from left to right, or in terms of distance from the nucleus, principal energy level.